dear students, welcome you all once again. I am Meghamala, working assistant professor from Electronics and Communication Department, Institute of Aeronautical Engineering. And today I am going to share about high level synthesis part 2. So in the previous class I have discussed about the part 1. In the part 1, I've shared something about the different tools that we have make use in order to design a proper module, and also about different steps how to consider the scheduling, or else how to allocate the peripherals and all. And now in this part 2, we will keenly understand about the designing of different things. So starting from the high level description of an application, an RTL component library and specific design constraints and high-level synthesis tools execute the following tasks. So here, if you are considering any tool with respect to the high-level synthesis, and then if you want to execute that tool in that particular module, then you have to go through all these 7 parameters, all these 7 steps you have to go through. So the first and foremost step is to compile the specification. So first thing is you have to compile the design specifications, and the second one is allocation. Allocation of the hardware resources. So we must allocate, after compiling, we must allocate the hardware resources, and this hardware resources, it includes the functional units, storage components, buses, and so on. Okay, so the first is all about the compilation. The second one is all about the allocation of the different fundamental functional units, and the third one is, after allocating, we have to go for the scheduling. Okay, this scheduling consists of the different clock pulses. So the scheduling schedules the operations to different clock cycles. Okay, the third step is to schedule the clock cycles. Then the fourth is, now after scheduling, first is compiling, the second step is about the allocating, the third one is about the scheduling. So soon after scheduling, what we have to do is we must bind all the allocated, or else we must bind all the considered hardware equipment, right? So first thing is bind the operation of functional units. First is all about the binding the operation. Okay, binding the operation of the allocated hardware allocated functional units. And the fifth step is binding the variables of the storage elements. So the storage elements, what sort of storage devices that you are considering, that storage elements you have to bind it. Okay, and the fifth one is binds transfers to buses. Okay, and so on. So the sixth step is to bind in order to transfer the data from the buses, from one different bus to another different bus, or else in order to transfer the data among the different modules, we must bind the buses. Okay, bind the transfers to buses. And then the last step is the last task we have to do when you are synthesizing by using hardware high level synthesis tool is to generate the RTL architecture. Finally, after creating everything, we have to generate the RTL architecture. So all these steps, in order to synthesize by using different tools, okay, by using different software tools, we have to go through all these steps. First one is compilation. The second one is allocating different hardware units. In the hardware units, we have to consider the functional blocks as well as storage memory elements, and also the buses. Okay, buses are meant for the transfer of information and the connecting purpose. And then the third step is about the scheduling, and the fourth one is binding each module. Okay, binding each hardware. That means the connection of each hardware modules has been done in 4, 5, and 6th steps. And the last step is about the generating the RTL schematics, or else the RTL architecture. Finally, we'll by maintaining, or else by considering all the above 6 steps, final step is will make it will make it into a proper structure. Okay, proper picture. That is all about the RTL architecture generation. And now we will see each and everything in we will discuss each and everything in particular. So here this figure is all about the HTL synthesis. So in this synthesis, first is about the specification. So specification, it means that in order to design some module, or else in order to develop some circuit, you have to be specific about the components that you are considering. Okay, so all the specifications, what all needed in order to build a basic blocks. Okay, the specifications should be considered first. And then coming to the compilation. So what is this compiling? Compilation means, as I said you, this is a compiled specification. So first is specifications. That means what? We will be considering all the specifications. After considering the specifications, now we need to compile. Okay, we need to compile. So we will see what is meant by compilation and modeling. So in the compilation, high-level synthesis always begins with the compilation of the functional specification. So it is a very first step that high-level synthesis tools. The first thing that it does is it will compile. Okay, it will compile the specifications that you have considered, and then the first step transforms the input description to a formal representation. So after compilation, it follows with the transformation, or else it follows with the transform. So whatever the variables, or else whatever the inputs that you are specified with, and after compiling, you will transform it. So you will transform it into a formal representation. That means what? You will represent each and every specification clearly in the code. Okay, each and every specifications will be transformed into the inputs. It will be transformed into the output. It will be transformed into the in outputs. So here, soon after the compilation, the transformations of the inputs and as well as the outputs takes place into a proper formal representation, And then this first step traditionally includes several code optimizations. So here, soon after compiling, that means after transformations, what it does is this will traditionally includes several code optimizations. It will code the optimizations. It goes different optimizations, individual optimizations and non-individual optimizations. So individual optimizations such as deadlock, or else such as dead code elimination. Okay, dead code elimination and false data dependency. Dead code eliminations as well, false data dependency eliminations, and constant folding and loop transformations. So after transforming after transforming the inputs into a formal representation, after giving the input and output, after showing the input and output into a proper manner, then what we will do is the first step is code optimizations. In this code optimizations, we will be eliminating all the unnecessary things which are present in the code. So that eliminations, it could be about the dead code elimination. Okay, it could be about the unnecessary omission of the unnecessary omissions which are present in the code, and also about false data dependency eliminations. So when you are compiling the devices, modules, what happens is sometimes without knowingly, some false data will be occurred. Okay, some false data can be seen in the code. So with the help of after transformation, we can eliminate this by using false data dependency elimination techniques, and then constant folding and loop transformations. And also in this compilation, after compilation, you may see the loop transformations as well. Loop transformations are nothing but the redundancy, the repeatness. Okay, the repeatness of the words or else of variables can be seen over here. So such kind of things can also be eliminated easily. So all this will be done in this area, compilation and formal model. Okay, so after this, we go with this formal model. So what is this formal model? The name indicates formal model is nothing but it produced by the compilation classically exhibits the data and control dependencies between the operations. So this formal model the formal model is produced by the compilation classically the formal model, it exhibits the data and control dependencies between the operations. So the formal model, we are obtaining this with respect to the compilation. First one is specification, and the second one is compilation, and the third one is formal model. So this formal model is nothing but it has some data, it exhibits some data. Okay, it exhibits some data and it controls it controls the data dependencies between the operations. So the data dependency, if between the operations, for example, I have 10 statements to be executed. So out of my 10 statements, sometimes what happens, as I said, if I'm aware, or else if I'm occurring, some unwanted data is being occurred in between statement 7 and statement 8. So what I want to do is, I want to omit this statement. I want to omit this unwanted data. Okay, I can eliminate this unwanted data, and so that the data it will controls. So the procedure will, the formal model, it controls the dependencies between the operations, the data and control dependencies between the operations, and then the data dependencies can be easily represented. So the data dependency, which if it is needed in between the statements, it can be, or else it can be easily represented with data flow graphs. Already in the previous class, we have discussed the data flow graph. Data flow graph is nothing but it contains the expressions with respect to the operators, different sort of operators. If we are considering any sort of operators, or among all these different operators, the data dependency, how it is depending, how the data is depending from one accumulator to the other accumulator. So it's all about the data flow graph, how the data is flowing between the switching of the data between the two or more operators, how it is happening, we can easily understand by this data flow graph. So the data dependency is easily represented, or is that easily represented with the help of data flow graph. In each and every node represents an operation, and the arcs between the nodes represents the input, output, and temporary variables. So here the data flow graph, it has some memory allocation, and also it has it has the nodes. Okay, so every node represents an operation. So each and every node, for example, I have A and B. So what I want to do is, whatever the information that I'm having A and B, I need to accumulate in a C. Okay, in the C memory, I must accumulate. So what I do is, I will fetch the data from A, I will fetch the data from C, and after fetching the data from A and B, I will accumulate all the data which is fetched from A and B onto the C. Okay, so in order to accumulate in the register C, I have to go through or else I have to perform some operations based on the operators. That means, for example, C is equals to A dot B, isn't it? Or C is equals to A into B, multiplicand operands. So by using all the operations, the node, each node represents, this is a node, each node represents the operation. So here I can, if I'm going with the, or else if I'm performing the operator upper hand, I can represent it with minus. If it's a multiplicand, multiplier, I have to represent it with multiplying. So the data flow graph, it will easily help us to represent how the data is flowing between the allocated task, between the allocated data, and with each and every node representing the operations or the operands. And now coming to the allocation. So allocation is a see here you can see the specification, compilation. After formal modeling, we are going directly to the allocation. So allocation, scheduling, and binding. Allocation, scheduling, and binding are together accommodated in a library. Okay, so allocation, scheduling, and binding all together are accumulated in a library. So in detail, we will be discussing what is meant by allocating, what is meant by scheduling, and as well as the binding. So coming to the allocation, always defines the type, and it defines the type and the number of hardware resources. So remember, allocation is nothing but allotting something, right? So if you are allotting some seats, or else if you are allotting some, allotting means just giving space, right? So allocation defines a type. So what sort of allocation is, what kind of it is. So it defines a type, and also the number of hardware resources. So the resources, it includes functional units, storage elements, and connectivity components. So here allocation, it defines about the type, first thing, And the second thing is it defines about the number of hardware resources, and that hardware resources, it is nothing but the storage elements, buses. Okay, storage elements, buses are nothing but the connectivity components. Connectivity components are in other terms I can say that the buses are nothing but where it connects all the peripheral devices, right? So the number of hardware resources and as well as the types. And then depending on the high level synthesis tools, depending on these tools, some components may be added during the scheduling and binding tasks. So we see that the scheduling, binding and allocation, all these three are present in the library. So here when you are synthesizing some product, or else when you are synthesizing some device, you have to remember that there is a chance of adding, alterations can be done. Okay, alterations, there may be a chance of adding during the scheduling and binding task, during the scheduling and binding, allocating, scheduling and binding. So in the scheduling and binding, there is a chance of adding or removing the data can be happen, and this can be done only when you are using the high level synthesis tools. And then for example, we see the connectivity component. So the connectivity component is nothing but the buses. So the buses, such as buses, see here, example for the connectivity components are nothing but the buses or point-to-point connections among components. So buses, what the purpose of the buses is, they connect the devices. Okay, all the peripheral devices which are present in the particular module. This buses will connect all the modules which are present in the buses. So the connectivity components can be added before or after binding the scheduling tasks. So here, in between the scheduling and binding, all the devices pertaining to the connectivity components, that means the buses, different sort of buses can be added or can be removed only after before or after binding, or else before or after binding and scheduling the tasks. So before or else after binding or scheduling the tasks, then only we can add the connectivity components. So this is what the allocation means. Allocation is something that you are giving. So the whatever you are giving, it could be in terms of connecting types, or else it could be in terms of memory elements or the storage elements. And all these things will be done before or after the scheduling or binding task, and not in between the scheduling and the binding task. And the components are selected from the RTL component library. So as I said the components which you want to add or else which you want to remove, they are selected from the library. Why? Because see, allocation, scheduling and binding, all these three are connected to the library, right? So from the library we can take the data. And the components are selected from the RTL component library, and it's important to select at least one component for each operation in the specific module. So here, one component from each module. So if you want to model different modules, or else if you want to alter different modules, so you can take one component from one module at a time. Okay, one component from one module from the library we can access at a time. And now coming to the scheduling. Scheduling is nothing but all operations required in specific mode must be scheduled into cycles. Yes, of course, scheduling is nothing but it has to be modeled. It has to be modeled whatever the specifications that you are considered. Okay, specifications, after specifications, compilations, after compilations, alteration and allocation. After compilation, we are going with the formal model. And after formal model, we are alerting and allocation is done. And after allocation, scheduling, and after scheduling, binding, right? So in the scheduling, what the scheduling talks about is all the operations required in the specification model must be scheduled into cycles. So the specifications which are modeled from this formal modeling or allocation or compilation, it has to schedule into different cycles. Okay, it has to schedule into different cycles. In other words, for each operation such as A is equals to B or C. So here I have to schedule this into different cycles. So what I can go is I have to the variables B and C must be read from their sources. So now as I said A is equals to B of C, right? So in order to schedule this task, what I should do is I have to read B and C. B and C must be read from the sources. So from their sources, they have to read first, and then they can write as well. So they either storage components or functional unit components. So how can they read or write from the storage components or else from the functional unit components? And after reading, okay, after reading from the sources, they need to brought to the input as a function of a functional unit. So first and foremost thing, if you are considering any word or else if you want to execute the operation, if you want to execute some operations, for example, here he has given A is equals to B or C, for example. So what we have to do is, first thing is you need to read it. Okay, so after reading, you have to read this B and C. Okay, B and C are the inputs, right? So you have to read it from the sources. Okay, after reading it from the sources, they from the different sources, B should come from the different source and C should come from the different source. So after getting it from the different source, we have to like after bringing into a functional unit, it has to execute. After bringing into a particular sources, it has to execute the operation op. So here I am representing B op C. That means what? A is equals to B multiplicand C, or else A is equals to B minus C, or else A is equals to B plus C. So first thing is we have to fetch what is B. For B and C we have to fetch from their sources, and then they have to brought it together. And after bringing it together, what I have to do is it can be executed. It can be executed as per the operator that you are assigned. See, it can execute the addition, it can have to execute the subtraction, it has to execute the multiplication, and then the result must be brought to its destination. So after see, in a diagrammatical order I can represent. See, I have to fetch B, I have to fetch C, right? So after fetching B and C, I have to bring B and C from their sources to a particular point. So here, as I'm considering A is equals to B plus C, I got this. So after doing the operation, whatever the result I'm getting, I'm storing in A, isn't it? So this is my destination. So after I have to bring it to the destination part. So the destination part is nothing but the storage or functional unit. So this is how the scheduling will be done, and all the scheduling can be explained very easily by using data flow graphs. Using data flow graph, we can easily analyze the scheduling of different tasks. Okay, and then depending on the functional components to which the operation is mapped, the operations can be scheduled within one clock or scheduled over the cycles. So as I said before, scheduling is all about the cycles, right? So depending on the functional component, so depending on the functional component that you are considering, remember that after mapping, the scheduling can be done within a clock, one clock cycles, or else it can be take more than one clock cycles. Okay, more than several cycles or one clock cycles. And then operation can be chained. What does this word chained means? Chain is nothing but I have some inputs and I got some output. So this output can be given as input to the second element. So this is the first element, and to the second element, I can give this output, whatever the output that I got from the first element, it can act as an input to the second element. Okay, and from there I will be getting the output. So this output again, it acts as an input to the third element first. Okay, third element. So likewise, this is nothing but the chained process. So here I can say the operations can be chained, and then operations can be scheduled to extent in parallel provided there are no data dependencies between them. So here the execution of the operations can go parallelly, okay, concurrently or parallelly. The execution of the operations can be done unless and until if there is no data dependency. That means what? In order to execute element 2, if I need any data from the element 1, what happens here is I cannot process the element 2 unless and until the data which I want from the element 1. So here, unless if I'm having the data sufficient in element 2, then I can easily process the data. So that's what it's saying. So there are sufficient resources available at the same time. So if in order to execute all the operations concurrently or parallelly, there are sufficient data which are available in the libraries, we can access them. Then coming to the binding. Okay, so binding is about each variable that carries values across cycle must be bound to a storage element. So binding is nothing but it must be bound to the storage unit. So the variables which carries, okay, the variables which carries as per the clock signals, it has to bind to the storage elements, or else it can be bind to the buses, or that means the connectivity, okay, the connecting devices, or else it can be bind to the functional blocks. Binding is all about it has to bind it, okay, it has to collect it. The collections can be with respect to the buses, the collection can be with respect to the functional blocks as well. And then in addition, several variables with non-overlapping or mutually exclusive lifetimes can be bound to same storage elements. So here he's saying that in other words, or else in addition, okay, in addition, several variables with a non-overlapping or mutually exclusive. If the data is not overlapping, if it is mutually exclusive, or else if it is pertaining to some operation, then it can be bound to the storage unit. Okay. Why it is bonding to the storage unit means the storage units will contains the operations, or else it contains the data which is needed to it. Okay, that's the reason we are saying that it is an additional advantage in the binding process, that several variables within non-overlapping or mutual exclusive lifetimes can be bound to the storage elements or a storage units, and every operation in the specification model must be bound to one of the functional units capable of executing the operation. So here in the binding process, we have to remember something, that every operation in the specific model, okay, in different models, every operation that you are considering, it must be bound to the functional units capable of executing the operation. So it must be capable enough of the functional unit. That means what is that functional unit is capable to bind the storage units or not. We have to or else we have to ponder on this very much. Before you're binding, you have to think that the functional unit that you are considering, is it able to bound it or not. Okay, this is one of the important point to remember in the binding process. And then finally, after binding, the last thing is generation. So generation is nothing but after binding, after specification compilation, what is this? Formal modeling, allocation, scheduling, and after binding, finally we are coming up with a new block, or else we are coming up with a new model. So generation is all about a new model. So once decision have been made in the preceding task of allocation, scheduling, and binding, the goal of RTL, that means the final purpose of RTL is generation steps. Obviously, all steps are design decision made and generate an RTL model of the synthesized design. So finally, we are coming up with a model, or else we are coming up with a design after scheduling, allocating, and everything, all the process. Finally, we are coming up with a new model. So this is all about the generation steps, or as steps which we need to follow if you are using the high level synthesis tools. And now we will see when you are considering the tools, you have to remember, or else you have to think more about the technology dependent optimizations or technology independent optimizations. Few optimizations we have to be very clear about it. So now we will see what are the technology dependent optimizations. So this technology dependent optimizations are additional library components. Okay, technology dependent. You just listen to the word carefully. Technology dependent. Technology dependent means the additional library components. More complex cells may be slower, but will reduce area of logic of and critical path. So here, additional library, it just contains variables or else a data which is slower. Okay, the complex cells may be slower, but it will reduce the area though it is slower. Okay, one of the disadvantages, the swiftness. Though it is slow, but what it does is it reduces the area, which is the advantage, right? So it reduces the area for logic of and critical path. And after that, load buffering. So load buffering is it adding buffers or inverters to improve load induced delays along the critical path. So in the critical path, in the critical path, the load buffering, that means what? Here we can add the inverters or the buffers. We can add the inverters in order to improve the load induced delays. In order to improve the induced delays, we can be adding the inverters, okay, inverter gates in the along the critical path. And then resizing. So what we have done till now, we have added some inverters or else the buffers. So after then we'll be moving forward to the resizing. Resizing is resize transistors in gates along critical path. And now is we need to resize. That means what? We have to get or else we have to consider the minimum number of transistors which are required in order to develop some module. Okay, if we in order to develop some module, if we are considering more number of transistor, okay, rather than that means what? For example, if I want to model a circuit, so in order to model a circuit, I need 10 transistors. But out of my knowledge, what am I doing is instead of 10 transistors, I am considering 15 transistors. So what happens is I have to omit the 5 more transistors. So here I can resize, I can reduce the size of that particular model using this resizing techniques along the critical path. And then retiming. So retiming is change placements of latches or registers to minimize overall cycle time. So retiming means we can change the timing constraint as well. So change the placements of latches. If we change the placement of latches or the storage devices, if we are changing the places of storage devices like latches, flip-flops or registers, and then we can minimize the overall cycle time. Okay, this is how we can resize or else retime the given constraint. This is one more the advantage. And then increase routability over or through cells. And next is after retiming, we can increase the routability, okay, through the cells or over the cells. So that means what? We can reduce routing congestion. That means what? We can reduce the trafficking between the devices. Okay, the routing can be reduced, or as a complexity in the connection between the connection among the peripheral devices can be reduced. So here, so as I can say that these are all the advantageous factors, right? So as these are all the advantageous factors, so the name I'm saying that the technology dependent optimizations. So being a designer, when you are designing some module, you have to keep in your mind that going to technology independent optimization, rather we can move or else we can consider the technology dependent optimizations, because there are several advantages where a designer can smoothly compile or else he can smoothly design a particular model. And now we will see here Verilog, logic synthesis, gate netlist, place and route, and mask. So this is a small diagram where you can easily understand about the Verilog or else the synthesizing tools about synthesizing tools. Now see Verilog. Okay, Verilog is a language that we are using. And coming to the logic synthesis, in this synthesis, by using different sort of synthesizing tools, okay, hardware synthesis tools or software synthesis tools, we can get rid of the complexity. And now we will see in the synthesis, logic synthesis, HDL logic, okay, hardware descriptional languages, hardware descriptional language logic. That means what? Using the hardware logic tools, synthesizing tools. Till now in the previous class, we have discussed there are many high-level language synthesizing tools, right? High-level languages we have come across. C, System C, okay, C, System C, Simulink and MATLAB. These are all the high-level languages. So, and after considering the logic, then map to target library. So, in order to synthesize some module, we have to always a library will help us to get the things. Okay, always the library map to target library. So we need to map on to the target library. Why? Because in order to consider the things or else in order to remove the things, this library plays a vital role in all the areas. Okay, and then optimize speed and area. As speed and area are the two different constraints where they play a crucial role in all the designing part, in all the designs of the basic building blocks. So we need to optimize the speed and area constraints as well. And after this, the gate netlist. So obviously, in order to module a particular circuit, we must have the circuit will be drawn with respect to the gates as well. So the gate netlist, the gates which are present in the library can be directly taken from the gate primitives, right? So soon after that, place and route. So this placing and routing, again, it's one of the crucial thing to be implemented wisely. If you are a designer, then it's your responsibility to considering the things and placing them in a proper place and routing with appropriate by using the buses and all. It's a very crucial thing, right? So in the placing and routing, you see, create floor plan blocks. Now, in order to place some peripheral devices, right, floor planning is needed. So create floor plan blocks, and now you have to segregate the place. Now you have to segregate the place into different sort of blocks, right? This is nothing but the floor planning. And place cells in blocks. So how many blocks, like you after segregating, place the blocks in different place the modules in different blocks. And then route interconnect. Route interconnect means for the connecting purpose, you must connect all the blocks. Then optimize, iterate. That means what? After connection, you have to see, is there any complexity is there or not. If you find any complexity, then there is a chance of reducing the blocks. Okay, being a designer, in the Verilog, we have a freedom that we can reduce the size, and we can reduce the size by not considering some gates. Okay, this is how the placing and routing takes place. And finally, after placing and routing, the mask. Mask is a layer. Okay, we'll be forming into a particular mask and layer, and then etching process will be done. And then after etching, proper shape or else a proper thing is coming to existence, and then finally packing and everything will be done. Testing and packing and everything will be done in the last steps. And now here there is an important note. So the note is about none of these operations is completely isolated. Okay, whatever the tools that you are considering for the synthesis process, so none of the operations is completely isolated from the target technology. Okay, so the target technology, none of the operations are isolated. Everything are into it. But experiences has shown it's advantageous to reduce the size of the problems as much as possible before starting. So here one of the advantages is we can, in order to reduce the size, this is one of the advantages that I can say. So this in order to reduce the problem, or else in order to reduce the size, the problem, if you are occurring anything, then we can resize it, or else we can retime it and resize it. So before starting the technology dependent optimization. So by using the technology dependent optimization, if there is any complexity in the building blocks, then there is a chance of resizing it. Okay, that means what, the complexity can be reduced. This is one of the advantages, and that advantages we can see only in the technology dependent optimizations, rather not in the technology independent optimization. So this is one of the important note to be remembered if you are designing some module. And then in some places, example, the ratio of the size of storage elements to size logic gates. So there is a ratio. Okay, in very few cases we have to go as per the ratio, and the ratio, it could be between the size of the storage elements and the size of the logic gates. Obviously, the size of the storage elements and the logic gate, the gate that you are considering, and the size of the elements, storage elements, is nothing but the flip-flop. The size of the flip-flops and the size of the gates are matters a lot. Why? Because as I said, you placing and routing plays a vital role. So we need to be pondered, or else we need to more cautious about the size of the storage element and as well as the gates. And our assumptions will be valid for several generations of the technology. So as this is one of the major assumptions to be remember, that the size of the gates and flip-flops or the storage elements are considered very cautiously. And coming to the technology independent optimization. So what does this technology independent optimization? So two-level Boolean minimization. One is two-level Boolean minimization, where based on the assumptions that reducing the number of product terms in an equation and reducing the size of each product term will result result in smaller and faster implementation. So you just remember that technology independent. Okay, this is not dependent on the technology. Technology independent optimization. That means what? This is another. This is another side of the technology. That is, here he is saying that the two level Boolean minimization. So the name itself says that the Boolean expressions, in the Boolean expressions, the min terms or the max terms, the product of sum or the sum of products. If you are having the, we can reduce the number of product terms. Okay, in the equation there is a possibility of reduction, or there is a possibility of minimizing the number of product terms and reducing the size. Obviously, when the number of product terms are reduced, obviously the size is the size we can get it down, right? The size can be reduced when the product terms are when the min terms are reduced. What happens? The size will be reduced. So this is one of the criteria that we can consider if you are going as per the technology independent optimization. And the second one is optimizing finite state machines. The second one is optimizing about the finite state machines. So already we have discussed about the finite state machines. These finite state machines will help us to convert the low level to a high level of abstraction, where we are using, there are two possible ways where we can implement this finite state machines. One is Mealy and Moore, depends upon the past input and as well as the present state outputs. So here, optimizing finite state machines, we look for the equivalent finite state machines. So equivalent finite state machines are nothing but that produce the same output given the same sequence of input. So equivalence finite state, equivalence, the name itself indicates equivalence means if you are giving the two inputs, obviously you will observe the two outputs. So the product, it's nothing but the equivalent of finite state machines, they produce the same number of outputs when the same number of inputs are given. Okay, and that have fewer states. So obviously it's all depends upon us. It's all again depends on us. If you are giving the less number, we will obtain the less outputs. If you are giving the more number, we obtain the more outputs. And then choosing FSM state encoding that minimize the implementation area. So here, this particular last criteria, it says that size of the state storage plus size of logic implement next state and output function. So choosing the finite state machine state encodings. So choosing the finite state encodings, that means what? Input, output, and as well as the size of the storage and also the size of the logic implementation. Size of the storage and the size of the state and size of the logic is nothing but it's purely depends upon the output that you are observing. Okay, so the choosing of finite state machine state encodings the minimize implementation area. So if you want to reduce the size of the area, then obviously you have to reduce the state storage to storage of the states, and also along with the size of the logic implementation of for the next state, and as well as the output function. So obviously if you think, or else if you find the similarities, or else if you find the differences between these two categories or else these two criteria, there is a lot of difference between the technology dependent and technology independent optimization. So as per my knowledge, or else individually if we think, everybody will opt for the technology dependent optimizations, okay, rather than going for the technology independent optimizations. And then we will see the simulation versus synthesis. So simulation versus synthesis is nothing but in the Verilog like VHDL, not everything that can be simulated can be synthesized. Okay, so there is a difference between these two names, simulation and synthesizes. So simulation semantics are based on sequential execution of the program. Simulation based on the simulation, just remember in an easy way, simulation is all about based on the sequential execution of the program with some notations of concurrent synchronous process, okay, with some synchronous process based on the sequential notation with some synchronous process. Simulation, sequence notations of some synchronous process. Obviously the simulation, if I have 10 statements, 1, 2, 3, 4 and 10 statements, how the simulation goes on, it has to execute the statement 1. and it will go then to statement 2. Likewise, it is based on the sequential executions. In sequence wise, it will execute. That's all about the simulation. And not all such programs can be synthesized. As I said it's not easy to specify the synthesizable subset of the HTL. Not all the programs can be synthesized. Few can be synthesized and few can be non-synthesized. Okay, and why we are saying that few can be non-synthesized means the errors can be easily finded out. And then, so in today's lecture, we will cross over, briefly discuss and emphasize. We will discuss what is synthesis and simulation, and we will emphasize, okay, we will exaggerate, okay, the difference between the synthesis and simulation. And infer logic and state elements. Okay, what is the logic? We have to concentrate on the logic. Infer about the logic, or else we have to concentrate the logic and the storage elements. And then perform technology independent optimization. Obviously, technology independent. Why? Because here we are considering the states, right? States and outputs. If it is with respect to the state, output, and Boolean function, better go with the state. Technology independent optimization, because here we have a logic specification, state assignment, right? Logic specification is about the Boolean expression, and state assignments. Okay, state assignments deals with respect to input, output, and next state. And then map elements to the target technology. So soon after going with this optimization, independent optimization, then we need to map the particular target technology. And then finally perform the technology dependent timing optimizations, because example, multi-level logic optimization and choose gate strengths to achieve speed goals. So in order to achieve speed and time, in order to achieve speed and area, okay, time is another constraint. In order to achieve speed and area, we can opt for time dependent, technology dependent optimization. Okay, in order to achieve speed and area, obviously we have to go with the technology dependent optimizations. Okay, so this is a basic difference between the simulation and the synthesis. And so today in part 2, we discussed basically about the process, okay, about the process of how the high level synthesis tool can be accessed. So it has to go through all the 7 steps, right from the starting, specification, and then simulation, okay, specification, simulation, allocation, and then after allocation, scheduling. It has to go through scheduling, and then after scheduling, it has to bind all the scheduling things, and then finally generating. So it has to go through all the 7 steps, and after 7 steps, being a designer, it all depends on us, what sort of optimization level that we are considering. If you are considering about the time dependent, technology dependent optimization, and this technology dependent optimization, it deals with the things about, or else it deals with the things about the compilation, no, not compilation. It deals about the additional library, load buffering, resizing, retiming, and as well as the routability increases. Okay, all these criteria, all these specifications will be seen under the technology dependent optimization. And non-technology dependent optimization is all about the reducing the number of states. Okay, reducing the number of states, reducing the speed and area constraints, and as well. So being a designer, it's all about depending on us what sort of which technology that you are opting for, whether it is technology dependent and technology independent. And also when it comes to the synthesis and simulation, as I said, simulation is all about checking out each and every statements synchronously. Okay, synchronously in a serial wise, it will be checking all about. And then synthesis, simulation is nothing but it is not needed for all the technologies to be done, but very few in some states we can say that not all such programs can be synthesized, but few problems can also be not synthesized. It can be, the errors can be found easily, and they can be manipulated easily in order to get the desired output. So this is all about the high level synthesis part 2. I hope you all understand. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.